Have you ever stopped to think if there's some kind of hidden language that describes how everything changes? You know, from a cup of coffee cooling down to the way planets orbit the sun? Well, it turns out there is. It's the language of differential equations. And today, we're going to pull back the curtain on this and show you how it's used to model and even predict the world around us. So let's dive in and see how this hidden language actually works. All right, we're not going to start by throwing a bunch of scary-looking symbols at you. No, we're going to start with something much simpler, something that, honestly, every single one of us has experienced. Just think about it for a second. You've made this amazing pot of soup, right? But it is way too hot to eat. So how long do you have to wait? Now, it seems like a really simple question, but the answer tells us something pretty profound about how our universe operates. Okay, let's get specific. Our soup is boiling, so it's at 100 degrees Celsius, and the room, what a scientist might call the ambient temperature, is a nice, comfortable 23 degrees. So we've got our starting point, and we know where it's eventually going to end up. But what happens in between? And this, right here, is the absolute key. The soup cools down fastest right at the beginning, when it's hottest, and the temperature difference is huge. But as it gets closer to room temperature, the cooling slows way down. The speed of change isn't constant, and to describe that, we need a very special kind of language. This is where we bring in the big guns of math. See, whenever you need to talk about rates of change, how fast something is happening, you need to speak the language of calculus. And here it is, a differential equation. All it is a rule. It doesn't tell you the temperature of the soup right now. Instead, it gives you the rule for how fast the temperature is changing at any single moment. You can think of it like a recipe for change. Now, I know this might look a little intimidating, but let's just break it down. On the left, that dt/dt, that's just a fancy way of saying the rate of change of temperature over time. That's it. And on the right, T minus TA is just the difference between the soup's temperature and the room's temperature. The negative K is just a constant. So all this equation is really saying is that the speed of cooling is proportional to how different the temperatures are. See? That's the whole rule. So we've got the rule, but what do we do with it? Well, this is where it gets really cool, because this simple rule lets us literally visualize the future. Because, let's be honest, solving these things with algebra can get really, really messy. Sometimes it's even impossible. But what if we didn't have to solve it at all? What if we could just draw the answer? The idea is actually pretty simple, but it's incredibly powerful. We can take our rule, our equation, and just plug in some numbers. We can ask, okay, if the soup is at 80 degrees, how fast is it cooling? Then we do it again. What about at 70 degrees and 60? At each point, we figure out the direction of change. So to see this in action, let's use a slightly simpler equation. Y equals y minus x. It's the same idea as the soup. We can just pick a bunch of points on a grid, plug them into the equation, and calculate the slope at every single spot. This table just shows the raw numbers for a handful of those points. And when you plot all of those little slopes as tiny arrows, you get this. This beautiful thing is called a direction field. It's like a map of ocean currents. It's not showing you just one path, it's showing you every possible path the solution could ever take. Which means finding a specific answer, like for our soup that started at 100 degrees, is as easy as dropping a little boat into the water at that starting point and just seeing where the currents pull it. You literally just go with the flow. Okay, this whole idea of writing rules for change, it's not just for soup. Not even close. It is everywhere. So let's zoom out for a second and see just how powerful this concept really is. For instance, we can model how a population grows, but we can also model how that growth starts to level off when it hits the limits of its environment, something biologists call carrying capacity. This gives us that much more realistic S-shaped curve, instead of just an uncontrolled explosion. We can even model how different populations interact with each other. Check this out. We've got lions and zebras. Now, look closely at that LZ term in both equations. For the lions, it's positive, right? Because more zebras means more food and more lions. But for the zebras, it's negative. More lions is, well, definitely not good news for the zebras. So through these simple rules, you can see it plain as day. The two populations are completely, fundamentally intertwined. You can't understand one without the other. Their fates are literally linked together in the math. And the applications just keep coming. The same mathematical language that describes predators and prey, well, it also describes the flow of electricity through a circuit, which is what governs pretty much every electronic device you own. It can model chemical reactions, industrial processes, like figuring out the concentration of salt in a huge tank as brine is flowing in and out. From biology to engineering to chemistry, it's all the same fundamental idea. Just describe the rate of change. So let's just step back for a moment and think about what all of this really means. Because this is so much more than just a clever way to describe things that are happening right now. This right here is the biggest takeaway. These equations are more than just descriptions of the present. They are engines of prediction. They're basically mathematical crystal balls. Think about it. If you know the rules, that's the differential equation, and you know where you are right now, that's your starting point, like our soup's initial temperature, then you can follow that map we made. You can chart a course directly into the future and predict what the system will look like at any time you want. And that leaves us with a final, pretty mind-bending question. If the cooling of your soup, the delicate dance of predators and prey, the flow of electrons through a wire, if all of it can be described by these deterministic mathematical rules, what does that imply about the predictability of our entire universe? It's definitely something to think about.